Hi, welcome to the 3.4 supplement video. In this video, we are going to be going over the 3.4 review and practice. We'll also go over the example problems after you try those on your own. And then finally, I'll remind you that you have to complete the homework practice at the end. Okay, so let's get started. Let's quickly review what a heating curve is. As you probably remember, heating curve is a plot of on the x-axis, you can have either heat or time. In this example, we have time that you see down there. Our x-axis is sort of in the middle of this plot since the temperature goes in the negative range. And then on the y-axis, we have the temperature. And it's important to note that it's usually at a given pressure, and that's usually at normal pressure, 1 atmosphere. Take a moment to write this down in your notes. Now, the reason why it's important to note the pressure is that the boiling points and melting points and the phases depend on pressure. So one real life example of that is if you buy a cake box mix from the grocery store, you may notice sometimes that they'll have the temperature at which you have to set the oven to bake the cake depends on the altitude. So they'll have usually a different temperature for high altitude, because if you live in the mountains at higher altitude, the pressure is lower. And so pressure affects the temperature at which something boils or melts. All right, so with that being said, in addition to pressure, and this is something I forgot to add on there, is that you're also given an amount. So I want you to add on to your notes and given amount, meaning that they have to give you the mass or the moles that you are measuring the heating curve. So in our example, it's 16 grams of methanol. So they tell us the amount that we're using when measuring this heating curve. Okay, so we know what a heating curve is. We now know how to read it. We've gone over that several times. Let's talk about what we can use the heating curve to do and to determine. Some of these things you already know. So some of the things you know is that you can use it to find the boiling point and melting point of a substance. Like, for example, here you can see the melting point of methanol is negative 97.6 degrees. And then for that of the liquid, it's at it boils at 64.6 degrees Celsius. You can also find the specific heat capacity, and that's the relative or actual amount, meaning that you can find whether the solid phase has a higher or smaller heat capacity than the liquid phase. That would be relative. You can also find the actual amounts if on the x-axis they're giving you the amount of heat added. So you could determine the actual value of the heat capacity if on the x-axis it's not time but heat. You can also use the heating curve to determine the delta H fusion and delta H vaporization, again, relative or actual amounts. So relative would say which one's bigger, the delta H fusion or delta H vaporization. Just a qualitative value would be, information would be given. Or you can find the actual amount, the actual value, like delta H vaporization is negative 50 degrees, negative 50 kilojoules per mole. And again, that would only be if the x-axis was given in heat added. Finally, you can find the phase at a given temperature. So, for example, here we would say at 100 degrees Celsius, methanol is a gas. And then you can use it to calculate the total heat lost or absorbed for a given process. And that you actually saw previously in the 3.4 video. So take a moment to copy this information down. Okay, so now you have 5 examples where you're doing those 5 things. It's not in this same exact order as written, so don't think that one is example one is finding the melting point or boiling point. So so take a moment to try. You want to try these problems 1, 2, 5 on your own, and then pause the video while you're trying it. When you press play again, we'll go over the problems one by one. Okay, so let's look at our first example. In the first example, they're saying the heating curve is recorded for 16 grams of methanol, and they're telling us the sample methanol is heated at a constant rate. Then which of the following statements is true about the delta H fusion, delta H vaporization? Okay, so the delta H fusion and delta H vaporization can be determined from the horizontal lines where we are undergoing melting or freezing, and that will be for fusion, and or evaporation, that would be for vaporization. And vaporization and evaporation kind of sound the same, so it's easy to see that those match. Now, what we typically, if the x-axis was given in heat added, that would be easy to see what we mean by using the heating curve to determine the relative values of delta H fusion and delta H vaporization. Because in that case, if the x-axis was the heat added, the length of this line would be equivalent to the delta H fusion, delta H vaporization. Just remember, delta H is heat at constant pressure. However, in this case, we don't have the delta H. Our x-axis is not in heat added; it's time. So that's the reason why they tell us here that it's heated. Methanol is heated at a constant rate. So what that means is that for a given unit of time, like for 1 second or whatever the unit of time is here, that is the same amount of heat. So for 1 second, let's say it's 50 kilojoules of heat added. Whether you're between 2 and 3 seconds or 4 and 5 seconds, it's always going to be 50 kilojoules of heat because you're adding it at a constant rate. All right, cool. Okay, so with that being said, we can just look at the relative lengths of both of these lines and see which one is bigger or smaller, or if they're about the same. And when I looked at this, they looked to be about the same to me. So the fusion and vaporization seem to be about the same, so I said they're approximately about the same. However, looking at it again, it looks like the vaporization may be a little bit bigger than the fusion, so it will be understandable if you chose B instead of C. But in this case, I chose C because they look to be about the same length. So just to recap, to find the relative amounts of fusion and vaporization, you look at the length of the flat lines where you're either melting or boiling. Okay, next one, true or false? The specific heat capacity of solid methanol is, that two should be only one is greater than the specific heat capacity of liquid methanol, and to explain. However, this one we're going to take our time a bit because specific heat capacity questions come up all the time on the AP exam, and because they're an opportunity for you to demonstrate not just your chemistry knowledge, but also your math knowledge as well. So let's start off by reviewing what specific heat capacity is. You remember from the Q MCAT equation, the specific heat capacity is a little c there, and it's basically the heat needed to raise the temperature of 1 gram of a substance 1 degree Celsius. So essentially what it's telling you is how much heat do you need to put in to a substance in order to raise its temperature. Some substances you need to put in a little bit of heat, some substance a lot. And it turns out the greater the heat capacity, the smaller the delta T, or the more heat is required for you to put in. So if you have a substance with a large heat capacity, you're going to have to put a lot of heat in order for the temperature to increase. One way of seeing that is by essentially rearranging the Q MCAT equation and solving it for C. And we're going to take out the mass just to make it easier as well. And if you do that, you divide both sides by delta T, and you get that C is equal to heat divided by delta T. And that sort of is going to help us to sort of quantify what we just said here: the greater the heat capacity, the smaller the delta T, or the more heat required. So what would that look like on a heating curve? So in a heating curve, we're actually plotting information. We're not using equations here. So what would that look like? Let's take, for example, if we have a large C. Remember we said if we have a large C, that means we either have to have a large Q, which is in our numerator, or a small delta T. And on the graph here, the Q would be represented on the x-axis. So if we want a large Q, we would draw a long horizontal line. And for a small change in temperature, we would draw a small vertical line since temperature is on the y-axis. Now, if you were to connect those lines, you would see that you would have this slope here in green, and this slope is actually a relatively small slope. So the larger C, the smaller the slope. And we know it's a small slope because slope is rise over run. So in this case, because our rise is small and our run is much longer, this is a small slope. So that's to say the larger the C, the smaller the slope. Of course, that means the smaller the C, the larger the slope. And we can also prove that as well. So for a small C, we would draw a short horizontal line for our Q and a long or tall vertical line for our delta T, and then we would see that we have a large slope here. So the smaller the C, the larger the slope. So now with that information, we can answer this question more thoroughly. Looking at the slopes for the solid and the liquid portion of the line, we can see that the solid portion has a smaller slope. So if it has a smaller slope, it has a greater heat capacity. All right, so our explanation here would be that this is actually true, and it's because the solid phase line has a smaller slope, which means it takes more heat to raise the temperature of methanol as a solid than as a liquid. That last bit, that it takes more heat, is important because that shows that you actually understand what heat capacity is. So in the AP exam, you can use the slope to recognize whether the heat capacity is larger or smaller, but you then still further have to utilize the definition of heat capacity to prove that you actually do understand what you're talking about. Okay, the next questions you're given at 273K methanols in what phase, and at 173K methanols in what phase. And this is sort of the question where you're figuring out the phases at a given temperature. Now, the reason why I added this one in was just give you an opportunity to pay attention to units. Notice that these are in Kelvin, but on our graph it's in degrees Celsius. So you'll have to use the K equals 273 plus degrees Celsius, or Kelvin equals 273 plus degrees Celsius to sort of convert your temperatures into degrees Celsius. And when you do that, the first one, that 273K is 0 degrees Celsius. So if we go along find 0 on the y-axis, we go along, boop, we see that we're in the liquid phase, so we can say it's a liquid. At 173, that's negative 100 degrees Celsius, so that's down here. And at first that may be a little difficult to see. You're like, oh, am I on the solid line, or am I melting? And remember, if you're melting, that means you would have two phases there. Solid and liquid would both be present if you were melting. So what we're going to use is we're going to use the melting point to help us figure that out. Notice that the melting point is negative 97.6 degrees Celsius. And since we're at 100 degrees Celsius, we're below that. So if you're below the melting point, you're in the solid range. And so we know it's a solid. The last one we're going to look at is what information do you need to solve the problem? Calculate the heat lost when 15 grams of methanol is cooled. And so for that, what I'm going to do is I'm going to redraw sort of this heating curve. And this is what we saw in the 3.4 video. So we're going from negative 50 degrees to, from 100 degrees to negative 50 degrees since we're cooling. And the first segment I have here where I'm going to gas, I'm going to use the Q equals MC gas delta T. So for that, I'm using that equation. For the second, I'm using the Q equals moles times delta H vaporization. And the last, I'm using Q equals MC liquid times delta T. So the pieces of information I need that are not given in this problem is the specific heat of the gas and liquid, and also the delta H vaporization. All right, so if you need more help on how to do this, make sure you rewatch the 3.4 video because it shows you how at each segment at the diagonals you're using Q MCAT, and on the horizontal portions of the heating curve using moles times either delta H vaporization or delta H fusion. All right, I hope you found this video helpful. Make sure that you complete your homework for practice. Have a quality day.